The focus this time is going to be on compressing or stretching things horizontally or flipping things horizontally. So same idea as the last time through. Go to your Desmos slider sketch. Make sure you've got it set in its default, so at 1100. And now do some experimentation. Which of these values change your compression or your stretching horizontally? So give that some exploration. I hope that you ended up with the same thing I ended up with. It's this one right here. It's the B that does that. So we know A is your vertical stretching, B is your horizontal stretching and compressing. So what we've seen is when B is 1, you've got a regular old sine graph. As you make your B bigger, your graph is getting compressed. And I hope that makes a little bit of sense. The B is inside the parentheses, multiplying your inputs. So if your inputs get bigger faster, that means you're going to go through a complete cycle faster. So the bigger your B, the shorter your cycle. Conversely, if you make your B a very, very tiny number, that stretches out how long it takes to get through a cycle, thereby stretching that graph horizontally. So let's go back here real quick. I'm going to put the regular sine function up for comparison. I'm going to change my scale here just so we can see that the typical sine function, that would be the orange one here, goes through one complete cycle. So up, down, and then back to the midline again over a distance of 2 pi. That's what we call the period of that function. So the period of sine or cosine is 2 pi. Corresponds with 1 revolution around that unit circle. Now for your transformed function, we know that it involves the b somehow. Let's see exactly how. When my b is 1, the period is still 2 pi. It takes from 0 to 2 pi to go through 1 complete revolution. Let's take b up to 2. So now I'm looking at the red graph and how long it takes it to go through 1 complete cycle. So up, down, and then back to the midline again. This time it only takes pi, so exactly half of what it was before. Interesting. Let's take the b now up to 4. Now the time it takes to go through 1 complete cycle, up, down, and back to the midline again, is 1/2 of a pi. So 4 times quicker than it used to be. So what I'm saying there is, if I go from 0 to 2 pi, so 1 cycle of the orange, the original sine graph, that's now 1, 2, 3, 4 cycles of our transformed graph. I notice that the b value is 4. Do you think that's coincidence? I certainly hope not, because it isn't. That's how you figure out your new period. You take 2 pi and divide by that absolute value of b. So on this particular graph, as I look at it, I can see that, hey, the amount of time it takes to go from the midline to the top, down to the bottom, and back to the midline again, well, that's a distance of 4. This graph has a period of 4. That means that my b value had to be pi over 2. Now, rest assured, you're not going to be expected to figure that out yet. That's something you'll focus more on next year. But what that means is this. The period then of this graph is 2 pi divided by absolute value of pi over 2, which is the same as 2 pi times the reciprocal of pi over 2, and you're left with 4. That's how you end up with that period of 4. Here, there's just another example of a compressed period. I'll tell you what, we'll deal with that one later. What I would like to do next is focus on what values of b do which things. So what types of b's flip your graph sideways? Let's start with that. Do some experimentation. So I notice that as I get bigger here, no, it's compressed, but nothing is flipped. It's when you flip things down into b being negative. That's what gives you that horizontal reflection across the y-axis. So once again, reflection happens when your parameter, so the b value, is negative. The horizontal stretch and compression. Let's see what the dividing line is there. So I'll put my regular sine function up for reference. So right now, this is a compressed graph because it's going through its cycles more quickly. Now now it's a stretched graph because the red cycle is taking longer than the orange cycle did. And now I'm seeing values again that are, okay, now we're compressed again. So where is the dividing line is the question. So for big numbers like 3.2, we have a compression. When b is equal to exactly 1, two graphs are the same. And now when b is less than 1, okay, now it's stretched out. So this is very similar to what it was in the previous case with the vertical stretches and shrinks. Your graph gets stretched horizontally if b is small. So if the absolute value is less than 1. Small decimal or fraction multiplied inside means it takes longer to get through a complete cycle, so the cycle is longer. If your b value is greater than 1, well then you're multiplying your x by a bigger number. It gets big faster. You go through your cycles faster. What you'll be asked to do in your practice is to look at the equation that's given and determine what the new period is. So you first have to be able to identify the b. Don't make your life complicated. It's simply the number multiplied by the e theta. So in this case, b is 8. There it is. So I can see here that's going to be a compression. It's going to cause me to go through my cycles 8 times faster than normal. The period is then given by 2 pi over the absolute value of 8. That's just 2 pi over 8. And reduce that fraction, that's 1 pi over 4. There's your new period. So 0 to pi over 4 gets you through one complete cycle of that cosine function. Now when there's a division here, I need you to recognize that theta divided by 6 is the same thing as theta times 1 over 6. That makes it easy to spot your b. b is 1/6. That means that I'm going to have a stretched out sine function here, so it's going to take longer to get through one complete cycle. So the period should end up being something bigger than 2 pi. So 2 pi divided by absolute value of 1/6. I do need you to know that dividing by 1/6 is the same thing as multiplying by the reciprocal by 6 over 1. And this just gives us 12 pi. So this cycle takes 6 times longer to go all the way through one complete period than did the original sine function. And it's because of that 1/6.